All right, thanks for showing up to the meetup, everybody. This is the Nerves Meetup. Happens once a month at the end of the month. You can find it on meetup.com. Meetup is sponsored by Redwire Labs, where we do firmware development with Nerves. We help build custom Nerve system, custom Nerves firmware. We also specialize in doing build root and Yocto. Nerves obviously being built on build root, and a handful of other fun stuff there. We've got Nerve systems that we publish to be able to help you with Nerves. So on top of the official Nerve systems published by the Nerves core maintainers, we also have these and I believe a couple others right now too on our GitHub if you want some other options to be able to play with. And other cool news that we've got, we were just able to come out with support for the Trusted Platform module. So TPM 2.0 is an open standard for trusted platform modules and other cryptography options. So for those of you who are familiar with like the AdTech crypto chip by Microchip, also called Nerves Key, this is another option kind of like that, but it's vendor agnostic. It's much more of an open standard. There's common Linux tooling to support this, and we've now got Elixir support and Elixir wrappers around that and an integration into the OpenSSL engine to be able to use this. So this is a chip that's available with a lot of newer embedded hardware. So you can start ordering this with more of the dev kits, more modern dev kits and things like that. So like the CompuLab box here, for example, has that option. I believe the Seed Studio Recomputer has a TPM option available too, and you can also order them standalone off the shelf. So cool to see that. One more option there, and it's also, we haven't quite tested it yet, but it should be compatible with Nerves Cloud, Nerves Hub, with everything we've seen so far. So if you need a hardware crypto solution, and for some reason you can't get your hands on the AdTech chip, this is another option to check out. Other announcements, I don't believe we have too many here, but just so you all know, Lars did give a talk recently on how to iterate fast on hardware with Nerves. So more of an entry-level primer to Nerves and things you can do with it, but he shows off a lot of the newer tooling in the community. I know some of the talks around this are slightly dated at this point. So he's showing off live books, new features with Nerves Cloud, and a handful of cool stuff like that. And speaking of Nerves Cloud, that is a hosted version of Nerves Hub. So there's been a lot of Nerves Hub updates happening. Nerves Cloud is the managed version of that. It's currently in early access for anyone who wants to check that out at nervescloud.com. And that being said, we'll go over to Joe here for the presentation tonight on beeps and ports. So thank you, Joe.
All right, so here's my presentation, beeps and ports, how to make everybody in your house hate you while working on a port driver for audio. So let me just kind of start out with a quote from one of my favorite people. It's Wendy Carlos, who said, one time, a nice blend of prediction and surprise seemed to be at the heart of the best art. And so that's the highfalutin version of sometimes you think you know what you want to do, and sometimes you don't know what you want to do until you've done it. So there's a little bit of that here. Wendy Carlos was a pioneer in electronic music. She produced something in the 60s called Switched on Bach. I don't know how many people are old enough to know this, but it was works of Bach composed completely on 60s era Moog synthesizers with patch cables and lots of tape machines and things like that. This has a Macintosh in the screen, so that was sometime probably around 1984. But she had been doing this from the 60s on. And if you know what Moog is, it's a pioneering electronic music, audio analog music synthesizer. She was definitely a collaborator with Robert Moog when he was kind of coming up with a way to turn technology into musical instruments. In addition to Switched on Bach, she did soundtrack work on the original Tron, not the one from the 2000s, but the one from the 80s. Kubrick's film called A Clockwork Orange, and a little bit of work on the first Shining that Kubrick did as well. So she's got some backing on her, and definitely an inspiration for a lot of things that I play around with. So anyway, let's go. Who am I? I'm an embedded and firmware engineer. I've been doing this for most of my life, and I'm probably older than everybody else here. I've had a chance to work with a lot of the big companies you've probably heard of before. And I've, tackled a lot of technical challenges, sometimes things I wanted to do and sometimes things I didn't want to do, but had to learn how to do it anyway. I was in an all synth band a long time ago. It turns out that I was much better at pressing buttons and turning knobs than I was making music, but that feeds into this a little bit too. I'm relatively new to the Elixir community with probably less than 2 years here. But I do love the technology, and that kind of leads into why I'm here. I first learned the Beam in Erlang in 2006 and just thought it was just solve so many problems that I wanted to do. But I didn't love the language so much, and I could not convince, even though I did kind of a proof of concept, replacing a whole bunch of, in that era, LAMP stack, Java, and PHP and Oracle and MySQL. I just couldn't get enough traction with management to have a lot of people learn this Prolog-ish language at the time, but I did like it. Then around 2023, someone mentioned Elixir to me, and I did not know what that was. And they said Ruby, and I wasn't excited about that either. But when I saw that it was just this wonderful front end to Beam, I got very excited about it. And I've been looking for opportunities to kind of enmesh myself in this community for a while. And so next step here. So anyway, I just want to put this slide up because it really, I think, really represents kind of my mental state when I'm doing things. I'm on the right a lot more than I am on the left. But anyway, we're going to see this here. There's a whole lot of I don't know what I'm doing, but I will boldly try to do it anyway. What I'm going to cover today is just a little bit of the basics for audio, if you don't know, just so if I start throwing terms around, we'll have some common ground. How I'm generating sound in these tools that I'll show, how I'm using some input devices, and then I'll show you Exsynthia, which is the latest name for the toys that I'm working on. And there is a little bit of a buyer beware. There's not much Elixir code here yet, but that's where I want to go with this. So some basics about audio. You probably know what a waveform is, but I will show some examples of this as we go through there. Waveforms are just, in the simplest terms, a single cycle of some audio over time that your ear perceives in particular ways. And in my tools that I'll show you here, I am generating all of these types of waves: sine wave, square wave, sawtooth, triangle, and waveform. Let me just do a little show off here. So this is what Alex heard earlier. Can you guys hear that?
Yes, we can.
Is that too loud?
Slightly on the loud side, but it's okay depending on how much you can or can't turn it down.
How's that?
That's pretty good.
Okay, and then we can do that as well. So that's a sine wave. Oh, I can show you a little oscilloscope here too. This is kind of a cool discovery on the Linux side, something called Exoscope, which can peek into sound sources on Linux, along with this nice tool called QJackCTL, which lets you wire your audio sources up to things. So here's essentially the oscilloscope input, and then my Exsynthia output that shows up here. So if I show this waveform again, you'll see something that looks like a sine wave on the little oscilloscope, which evokes this sine wave that I mentioned before. I'm going to turn the volume way down for the next one, which is a square wave. Sounds a little bit harsher. Here's a sawtooth wave going one direction and one going the other direction, which doesn't sound different, but we'll see a use for that later. And a triangle, which sounds terrible. Oops. I take that back. That was me changing the volume, not the waveform. And there's the triangle. And to rest your ears, I won't play the white noise waveform. Um, but I just wanted to give you an idea for if you hadn't seen this before, an idea of what these different kind of waveforms sound like. People tend to think that sine waves can sound bellish, square waves can sound like a reed instrument. Sawtooth is kind of a less harsh version of a square wave, and a triangle is a more harsh version of a sine wave. I do have some custom stuff that I'll show you later on, but for I think what you might call just sample playback. Uh, some other basics about audio would be changing the frequency or the pitch. Pitch is represented as hertz, which is the same thing as cycles per second. Western music is based on something called a 12-tone scale, where you might recognize this as the A, B, C, D, E, F, G with the sharps in between. An interesting thing that was, and there's much more history than I can articulate here, but the choice for a nice round number on the piano was what's called concert A or A4, which is 440 hertz. And that's what you were hearing on this side. It was a 440 hertz waveform. The interesting thing about the 12-tone scale system is that octaves, when you go from an octave to the next higher up octave or lower, it's either twice the frequency or half the frequency. So in terms of math things, 440 is a nice number because it's easy to divide by 2 down to, for me at least, to 27.5, and multiply by 2 to go up to hertz, that is, and multiply by double until you get to 1760 hertz, which I can't remember how many octaves that is above the center of the piano keyboard. But the 12-tone scale just means that from A to G, that there are 12, they're not equal steps because there's some logarithmic nature to this, but there's essentially 12 steps between that place where you double the frequency. Another aspect of audio is amplitude, which probably makes sense to everybody, but also known as volume or gain if you're increasing it, or attenuation if you're not, if you're lowering it. And perception of volume is not linear. I don't know why I mentioned that here, because I don't, in my own tools, I'm just kind of using linear numbers for all of my audio amplitude changes. And then as far as computer audio generation, there is this concept of modulation, where you use something to change an aspect of another waveform, either by changing its frequency or changing its amplitude or changing filtering. The tools that I'll show here, I can change with this Nomu Jumbo that I'm typing over here. I can change the volume level, not in a modulation style, but basically in a direct style. But I will show somewhere a little bit later on where I could use the waveforms in my own generator to modulate the frequency of other waveforms. And if you RF or radio people might think that I'm trying to reinvent FM radio, that's not exactly it, but we'll get some interesting sounds out of it nonetheless. On to how I'm generating sound on these tools. I've gone through a couple of iterations with this actually not a couple of iterations. This is actually the 6th prototype that's been essentially rewritten from scratch, because nothing's ever exactly what you want. But on the categories of sound generation on Linux, there's something called ALSA, which is the Advanced Linux Sound Architecture, and it's kind of the lowest level of the audio stack on Linux. It's not entirely true. If you're on a Raspberry Pi, you can, there's something that's called an I2S port that you can just clock out data directly to a speaker essentially and bypass things. But it's rather timing dependent. So it's nice to have the infrastructure of Linux in place to kind of deliver the data to the respective parts in the right way. In the Linux community, you may have heard of Jack and Pipewire, and I think there's a couple of others. Those are higher level abstractions, but they're usually just layered on top of ASLA below that. Um, on I just want to take a little detour on Mac. There's the lowest level of that is called Core Audio. I've first wrote my own layer to talk to ASLA on Linux, and as I thought about wanting to run this on my Macintosh, I almost hand wrote that there, but I abandoned it because of something that I'll mention in a moment. On Windows, there's an equivalent to ASLA and Core Audio, which is called Direct Sound. It's also kind of the lowest. It's not absolutely the lowest level, but it's the lowest level that you want to handle for most application writing. And I definitely didn't want to handwrite something there because of this neat project called Mini Audio. Mini Audio is a single header file for C programs that will essentially let you enumerate all of the audio playback devices on your system or all your audio capture devices on the system, and gives you a simple way to just provide essentially a data callback that feeds the samples to the sound drivers so that you don't get glitching, and assuming that your callback isn't terribly inefficient, which I'm working on the fringes of making a very inefficient callback, but it will simplify you to have essentially an inner loop that would deliver audio to the hardware that's in place. So I have taken out my original ASLA only code and replaced it with Mini Audio equivalents. So that at this point, this code runs on Linux and Mac OS. I haven't had the courage to port this to Windows, but it's not too far away. I just have to change a little bit of threading model to make that work properly. I've got a next section of my slide that I call input devices, and I don't want to confuse that. I'm not talking about audio input devices. I'm talking about devices that you might use to control the generation of audio. The first that I will mention here is a console interface, which is what I'm doing over here. This is just a console program with some command line history and a little simple grammar that I've adopted and modified from another project for my own purposes. And I just say that this is a way to play with audio with low fanfare. If anybody here has seen Sam Aaron's project called Sonic Pi, his stuff is layered on top of another project called Sound Collider, I believe, and it's got a rather exotic programming language that goes along with that. It wasn't for me, so I have made my own version of things, which is very terse. Just a side note, I'm a VI user, so 2 or 3 character things that do other things are kind of a sweet spot for me. So you'll see that reflected in some things that I'm typing as I go along. The strings that I'm typing on to generate audio, though, they're not strictly my own invention. One of the early versions of my playing around with this was looking at another project called Amy. By the way, I'll try to put all the links to these things in a slide in the slide deck as I edit it and present this later on. So don't worry if I gloss over something too quickly. But there's an open source audio project called Amy, which does way more than what I am doing, but it didn't do it exactly the way I wanted to do it, so I rewrote my own. But they came up with this kind of simple ASCII 3 or 4 characters to produce elements of audio. They call it wire protocol. And it's just characters strung together that have a little bit of semantic use. I'll step through this one just because you'll see me typing parts of this as I go through. There's usually a alphabet letter. In this case, V means I want to do something with a voice, and I enumerate which voice it is by the next character. So this means voice 0. And then I want to give voice 0 a parameter. So W means set the waveform of the voice. And then there's a number that follows that. In this case, 0 means sine wave, and that's what you have seen. You saw me step through some of the waveforms over here. The next sequence here is F, which means set the frequency, and then it's followed by a number. In this case, it would be 440 hertz. The next step, which this is a little bit of an eye chart, but L is a shortened version of, well, not a shortened version, it's a mnemonic version of velocity, which is a kind of a keyboard term, which roughly means I want to set the amplitude. Velocity is kind of an homage to how MIDI keyboards work, because you can press a note on and then provide a velocity that is supposed to be representative of some volume change to the thing that you're playing back. So in short, this means play a sine wave at 440 hertz with an amplitude of 1. In my console output, I use a nice little open source project called Line Noise for command line editing. It's not like the MIDI audio, and it's just a header file, but it is a header file and a C file, so it's very easy to add to your C project without having to load a bunch of libraries or things like that. And I just say that because you can command line history up, and you can, the history of commands that you've typed in this console, they're stored so that when you start the application again, they're there for use. It has a little bit of a REPL feel, if everybody knows what a REPL is. I guess if you're using Elixir, you probably know IEX is the REPL there. So other classes of input devices other than the console, would be a serial port. I'm mentioning serial port for a very specific reason. There were some conversations on Elixir Conf about where John Cotton wanted to use, hey John, I see you on the call, by the way, wanted to use MIDI in some of his Nerves projects, which the ALSA project has some nice MIDI tools, but I was too lazy to, and this is a theme for you guys who've seen me at the Nerves meetup. I've been too lazy to recompile any Nerves distribution from scratch. So serial support is built into to most Nerves implementations, and I happen to have this little opto isolator and MIDI style port adapter that I was able to use with a FTDI USB to UART adapter. And interestingly enough, I didn't realize this, but there's a 5-volt pin on this FTDI adapter, so I'm able to power my optical isolator with the dongle as well. So it was kind of a nice little side note. But anyway, it winds up being serial, even though we're talking about MIDI. It's a serial data stream, and it was very easy for me to coerce my Nerve system and then my desktop Linux system to talk to it without installing a bunch of drivers or understanding how the MIDI tree works with ALSA, which I didn't want to understand that. Although, side note, this QJack CTL apparently gives some nice routing tools so that you can visually know how to connect things together. I haven't worked with it at all, but I was surprised to see that was populated based on when I hook another device up to this. So the real input device that I want to talk to via that MIDI interface is this old Rock Band 3 keytar, which I had in the closet forever. And it has a nice little MIDI interface off to the side. Basically just about 2 octaves and 1 key, but that's enough for playing around with. I wish I had a better demo than what I'm about to show you as far as making sounds, but I thought I'd just throw this out here anyway to show you that I am. Let's see, and I apologize for that, but this was just easy to hack together without using a server inside IEX. And so off to the side, I'm going to power this on. This keytar that you're seeing in this picture, but not live on video, and show you that. Let me just skip down here. I'm hitting the C key on the system, and when I press the key down, you'll see that I'm decoding some of the MIDI streams here, but that's a note on for MIDI channel 0 of key 60. And there's a velocity value. I'm holding down the key right now, and when I let up on it, you'll see that I get a note off message for the same key with a velocity associated with it. I'm going to press the same key really fast and look at the velocity value that you see at that point. Let's see, it went from 117 to 124, which just implies that I hit it harder. Anyway, this is a characteristic of MIDI is when a key is pressed down and when it's released. And they're divided that way so you can do chords where if I hit C and G together, they don't arrive at exactly the same time, but they're both on, which would be communicated in some future iteration of the code that I'm showing you today, so that you would give the illusion of the two notes being played exactly the same time. And I can let one up and then the other up, and they operate kind of independently. I think a lot of traditional ASCII keyboard controllers work the same way, where you don't just get a single message for a key press, but you get a press down and a release information. But normal keyboards don't have velocity with them, so that's kind of a nice little side note. I'm going to stop this Python program because it uses almost all of my CPU time because it's Python. I don't know any other reason than that. I did want to mention that I talked about this amazing A4 or 440 hertz as being kind of what's a kind of standard place to start from frequencies on a keyboard. In MIDI world, that's A440 corresponds to note number 69. And I don't know, for people who are not familiar with MIDI, what it actually is. MIDI does not specify directly what sound comes out of a key press. It just says that the key was pressed, and the sound generating hardware is up to decide what happens when that is pressed. So, you might have a keyboard where you press note number 69, which is concert A, and it plays a rooster sound, or it might play a violin. There's nothing in the MIDI notation itself that directly tells you what sound is going to come out as a result of receiving that note number. The last class of input device that I'm interested in is would be Erlang term format, because if in the incarnation where I have my final version of this, or a future version of this tool that I'm showing you, I do want the Elixir process to do a little bit better than this ASCII protocol for sending things back and forth. Because while setting frequencies and waveforms is kind of easy to do with a couple of ASCII characters, sending an entire waveform is a little messier, and I thought it would be rational to be able to send an array of sample values that would travel from the Elixir controlling process into my sound playback system. Or conversely, if in another future version of my tool, if you were using my tool to do a capture of an audio waveform, to be able to transfer that waveform out of my process back into the Elixir controlling process. So I've ignored a lot of people here and went ahead and wrote, instead of using the standard free, easy to use library that comes with Erlang to do a term format, I wanted to be like the cool kids, like the Mini Audio and the line noise people, and have my own header-only version of ETF parsing, so that you didn't have to know where the libraries were. This is a silly proclivity that I have for things, but I've done a pretty good job with this. It is a greedy camper onto standard in and standard out, rather than being a state machine. If Ben Murphy was here, he would say, write a state machine, which I definitely need to write a state machine for this, so that you can feed characters from whether it's a UDP port or a TCP port or, whatever. We'll get there, and it'll be delivered with the source code for Exsynthia in the meantime. In a previous incarnation of this software, I was using this term format to ask Mini Audio what devices were connected, and then choose one of them for playback, and then ship a waveform to play on that. And it was a really big learning experience, because beyond parsing and producing ETF, the behavior of port programs is a little finicky. That is, if you're unexpectedly, if the beam decides that it's time to not talk to you anymore, you don't necessarily get a graceful warning that everything has been shut down. So you can wind up with zombie processes that are holding onto ports. So I've got a fair amount of stuff that I probably didn't need to write, but wrote anyway, which tries to detect when I've been orphaned and tries to clean up and not chew up CPU time. And then I show you kind of the examples of things that it will parse. But there are things, it starts with a tuple, and it starts with the tuple's first element has to be a string. And then there's some variations on what it takes for. So it's not a complete parser. It's a parser for the minimum set of ETF that I thought I wanted to handle. And who knows, it might grow into something bigger than this later, but that's kind of the plans for now. So what this is all kind of leading up to in this presentation, and what might cause a lot of anxiety for my family as they hear tones coming out of my room all the time, is this project that I'm calling Exsynthia, because all the cool Elixir projects start with X, and I didn't want to camp on something else that someone might have done. X audio was a obvious choice, but I think someone might have camped on that already, and this does a little bit different things than what a strictly audio only driver would be. But the story is this: Exsynthia is actually the sixth complete rewrite of my sound generation tool. The first one was strictly based on that Amy tool that I mentioned in the background in C for Mac OS, and used Grand Central Dispatch for its threading model, if you guys have ever written any Mac OS programs. And then with some nasty pthreads emulation of Grand Central Dispatch on top of that. And I wasn't happy with that, so I did half of an implementation in Zig, because everybody wants to learn Zig. That didn't go very far, and then I completely renamed it because that incarnation was called a tool called Rototum. There's videos of me rambling on about this tool called Rototum. The rewrite into Zig became a project called Rattle, because it makes a lot of rattly noises all the time. And various other things. I've written it in Go. I've written it in TCL. There's been a lot of, I guess, maybe signs of OCD or some other behavior that's just like, hey, let's see how we can do this today. But my whole kind of the model here is that I want it to be a standalone process, because sound generation is a little bit of a sharp tool. You want to be able to do things quickly enough to deliver audio to the drivers. And so I play fast and loose with memory protection inside the processes. I've got threads that just basically jam values into arrays. That is probably not the best practice. And I do not want to be responsible to kill someone's beam by doing that. I'd rather my process fall over and the beam keep running, rather than this be a strictly linked into your beam process. It's probably going to be that way for a long time until, well, I think it's always going to be that way. And the high level control would be via this wire protocol with, if you're on the console, just directly typed in, or if it's using port via the ETF format that I mentioned earlier. So on to a little bit of demo of this. So you've heard some pieces of this before, but let me just kind of step through this a little bit more completely, because you saw me in the demo or in the slide earlier, where I did this incantation. And once again, that says for voice 0, use waveform 0, generate a tone at 440 hertz with amplitude of 1. And you'll hear that happen. What I didn't mention is that in the current version of this, there are 24 oscillators or voices that can be used at the same time. So I can do something like this and say voice 1, wave 0, frequency 441, amplitude 1. And this is just a little bit out of tune of the other one, and you'll get this interesting little beating behavior. And if you look at the waveform, you can kind of see you've got this interesting little up and down. the further out of tune this is, just a side note, my little protocol here, whatever the last voice you specified, any parameters you type in at that point are reused. So if I type F444, it will just change the frequency for that voice one. And you'll hear how it kind of has a faster beating system. Also, I mentioned, in addition to frequency, of MIDI note numbers. And I think I mentioned that note number 69 was supposed to correspond to A440. So I can type N and a MIDI note number 69, and this will put this back in tune. This will set the frequency to 440 again, and it's back in tune with the other waveform. The idea here, well, once again, this is just kind of adopting the AMI wire protocol notation. They do the same thing. But this kind of makes, if you're trying to map keyboard presses from a MIDI device into this, there's a little less math that you would have to do to make this take place. An interesting thing that MIDI does not support, though, but I do, is if I type 69.1, it can understand fractional numbers where MIDI absolutely does not. It's a 7-bit frequency or note number that's used inside MIDI. Can everybody hear me over this racket that I'm making, or do you guys hate me already?
No, we can hear you over it.
Okay, great. So here's, okay, as I mentioned, there's 24 voices. It's a compile option to see how many voices you want to be able to add together here. And in the inner loop of the audio generation stuff, it's just a for loop that says how many voices you define, do the math for all of those voices. By the way, the inner engine for this synthesizer is probably less than a page of code if you printed it out. So it's not too complicated. The clicking that you might be hearing this audio, I promise you it's not my software. This is an artifact of running this through Zoom. I noticed this earlier when I was testing all this out before. So not too much clicking. I'm doing pretty good in the sound generation capability. Okay, so let me do something. I'm going to stop both of these voices. So that's voice 0, amplitude 0, voice 1, amplitude 0. And I will shut this up. There is a lag between what I type and the audio changes here, and that's less present when you're on the system and more of an artifact of how many miles the audio is traveling to get from my keyboard to your ears. So I have my audio buffers kind of tuned to where it's not perfect latency between when you tell the engine to change something and when it happens, but it's much tighter than might be evident from this presentation. A little nomenclature that I've added to this is the ability to load arbitrary waveforms into the system through this. I'm not even going to try to explain this. It makes perfect sense to me because I wrote it. But this, behind the scenes, this is taking a standard wave file that's named o24.wave and loading it into the system. And you can kind of see as a response from that, it's going to do this. I'm going to use voice 2, and waveform 7 is called PCM. That's essentially for arbitrary waveforms in here. I want to play this back at, I want to say that the base frequency of this is 440 hertz. The frequency of this is not 1-to-1. This is just kind of a base number for what we're saying for the frequency. And I want to play this at amplitude, we'll say 3. Oh, sorry, bad demo. What I should have done is I didn't tell it which waveform to use. I can load 24 waveforms into the system, and that nomenclature said, let's MP24 was what the hint there was, but I didn't say which PCM wave I wanted to use, which is using this notation. And what you'll hear is just this looped wave playing forever and ever and ever. This is a BBC sample. If you guys have ever looked for sound effects, the BBC has a wonderful selection of things. And this was just nice to play around with. But I can change the frequency of this just like everything else. So you can get the expected bizarre sound effects. I can play it. That's half the frequency and then double the frequency. And if I wanted to be one shot, this is my nomenclature for this. So that says when it gets to the end of the waveform, it doesn't repeat. So now if I play it again, you'll see it just plays it one time. All right, so that's kind of some basic aspects of what Exsynthia will do with audio. I mentioned something early in the presentation about being able to modulate sound with other waveforms. And I think probably the way to show this is just to type some stuff and let you hear it. So I'm going to start on a new set of waveforms. I'm going to use a sine wave at 440 hertz for amplitude 1. I've heard this before. This is just using a different voice. I'm going to start another waveform with a sine wave at a lower frequency and a lower amplitude. And then I'm going to switch back to voice 3 and say this F means modulate its frequency based on the oscillator number that's specified next. So I'm just I want to use oscillator 4 to modulate the frequency of oscillator 3. And you'll get this strange effect where it's changing the frequency over time. If I look at voice 3, you'll see, or excuse me, voice 4. It's oscillating or modulating this at frequency 10. If I do it at something much lower, you'll get something of this nature. Or going way down, you can make these long sweeps of frequency. And this is modulating this by a sine wave. I can change it to a square wave, which doesn't sound so exciting. Oops, W1 is sine wave. And it winds up being really low frequency on the low end of the sine wave. There's a sawtooth wave, which kind of gives you an interesting effect. Let me make the frequency a little bit higher than this. Oops, I don't even know my own nomenclature here. I wanted to say waveform 2, which is a triangle. And it's this falling frequency behavior. The opposite of that is a sawtooth going the other direction. And then there's a triangle wave, which is W4, which kind of sounds like the sine wave, but it is a linear path. Now, it gets really interesting when you make your oscillator, your modulator frequency in the audio, at much higher frequencies. Let's just put it that way. So if I modulate this, or change the modulator frequency to be high, you'll get something that are variations of the sine wave, but they're have kind of some different sonic qualities to them. If you look at the waveform, you kind of get this thing that doesn't look like a sine wave anymore, and it's changing over time, so it sounds a little bit more interesting than just a plain sine wave. Changing the amplitude of that modulator gives you different effects too. Like if I make it really crazy, you get these harsh sounding things. So anyway, I've had just a blast playing with this. It's like the synthesizer I wanted when I was a kid. And it goes a little deeper than this. I'm going to shut all of this off, by the way. You can have modulators that modulate modulators that modulate modulators, and you can just get some very, very stacked up, interesting things. I think this in conjunction with having the MIDI keyboards connected to it might make a nice little interesting tool. So that's That's Exsynthia. That's what I've been spending my weekends driving my family crazy with. A side note for anybody who's written audio software before, the reason that my family is annoyed by this is when you're writing software the first time, wearing headphones is sometimes really terrible. And I've, had, 20 kilohertz waveforms hit my ear at full volume, and it's just not pleasant. So I tend to put this in my office with the door closed and do it that way. But yeah, it doesn't make me the most popular person here a lot of times. Okay, so where am I going with this? And this is really just for my own pleasure. But if anybody else is interested and wants to collaborate with me, I'll certainly work with you. I think I've mentioned this before. I want to have full control via Erlang term format because I want the Elixir process to kind of do the organizational thing of this. I want to go back many, many, many steps. I think I told you how the synth engine is a little loose and wild and loose with how it handles arrays. All of the state and the setup for waveforms is in a large table that you can just poke values in randomly, and it kind of changes the behavior of the synthesizer in that case. And it winds up just being this big rectangle of C unions. The idea there, instead of having a fancy structure that might be a little bit more elegant, was I've got a mind towards a way of using GPUs to encapsulate versions of the waveform, so you can have a kind of succinct representation of that and being able to break it up easily among pieces. But I think in the realm of just way out in the future, where Erlang is controlling a whole fleet of these little synthesizers around a room, it might be nice to take that entire row of an oscillator that exists in one state in a row at a table and transfer it to another system. And since the entire state of that oscillator is kind of encapsulated in one easy place, distributing it to other sound generating nodes in the system would be easy in the kind of structure that I put in place there. But that was a little bit of a detour. Future plans are I want to have more control of the oscillator, because what you're not seeing here are in the synth world is something called an envelope, where you would have the kind of the sound dynamics that maybe a piano has, where it can be soft in the beginning and the volume slowly rises up, or it's a steep ramp up to full amplitude. That's something that I know how to do. I just haven't done it in this version yet. If you look at some of the videos on the previous incarnations of this, which are Rototom and Rattle, I have what you could essentially call a drum machine in there, where sentences of this wire protocol are played in sequence, in parallel at different times. So you get the effect of having, a drum machine with many different steps in it. Maybe if Alex lets me present again in a month or two, I'll show you what that looks like in a future version. Since this is Linux based and Erlang based and Elixir based, I've run this on the smallest Raspberry Pis, and it seems to be able to keep up with my little loop there. So I can see a little place where we have some, Raspberry Pi synthesizer device that's powered by this. And that long talk about how I structured the kind of inner table for sound is what I'm talking about for the multi-device synchronization, where it would be easy to take the state of an oscillator from one piece of hardware and move it to another. All right, so way back in the beginning of the presentation, I kind of gave you this dichotomy of the two states of every programmer, and I said I'm probably more on the right than I'm on the left. But I think there may be two more states that I would throw this out as kind of my punchline for the whole thing. I think there's some other states where it's I have a little bit idea of what I'm doing, and I'm not a god, but I'm pretty cool nonetheless. And so that's the punchline. That's where I'll leave it. Hey, look, this is that synthesizer guy from a previous era. So thank you all. I hope there's something to be learned here. Reach out to me if you're curious about anything.
Awesome. Thank you, Joe. So anyone who has questions for Joe, feel free to unmute yourself now and ask away.
Super cool to see, Joe. I was gonna ask you to jump into some source code, but then I just kind of Googled around and I found it, so I'll do that myself. Um,
Okay.
but yeah, really fun to see.
Yeah, thanks for the inspiration on the MIDI stuff that I didn't use, and I just went off and did the old UART version of things here. But we'll get to it.
Thanks for the reminder to publish my MIDI 1.0 library. That's just UART.
Cool.
Dang, Amelino just ran away. Amelino does a ton with ports, and I was going to see what he thought and have him pick your brain on what you were doing going into the Erlang term format and stuff like that, because
I
that's an
think I
interesting
think you'll
world.
be largely offended by the way I'm doing things because I am, but it's fun to kind of see the bits flying back and forth from out of Erlang for sure.
John, maybe quick question is to put you on the spot since you mentioned the MIDI thing, and that's really related to this presentation. What all have you been doing with MIDI and nerves for anybody who's interested in that library?
Yeah, so I guess a few meetups ago, really just two meetups ago, I kind of showed up and crashed with my problem of trying to get like MIDI USB working. And it just turned out if you add a few build root packages for like some of the ALSA utils, uh, you can use, one of the libraries that I was hoping to work with. So I have a fork going. I don't know that Frank wants all the extra stuff in there to support it, but I've kind of toyed with the idea of having like an Elixir audio or like a Nerves audio fork that has like some of the extra packages in there to support it. But yeah, like with just like a little bit of extra work, I have like a custom system that can build, uh, the MIDI, the USB MIDI libraries that I was wanting to work with. And then, yeah, just more follow up probably with Joe about like some of the extra stuff we can do there. But it seems like there's some interesting possibilities on that side, on the audio side, for sure.
Yeah, and side note, there is some leftover garbage where I was talking to ASLA directly for sound. I did talk ASLA directly for MIDI, and there's it was possible to do that to essentially make my program just respond to whatever MIDI devices that it's connected up to. Um, and I think the conventional wisdom is to use FT, MIDI, or whatever. But I'm stubborn in certain ways, and the ASLA MIDI interface is actually not that bad. I like it better than what is it, FT MIDI or whatever, or Port MIDI is the other one. For one thing, FT MIDI is written in C++, which I have my proclivities about not using C++ as well. But uh, we can look into that because I think we might be able to come up with a nice little XMIDI interface that didn't have all of the garbage that I've got inside Exsynthia at this point. So
Did you? I'm trying to remember the project, and I probably should have prepped. I probably should have looked it up before the call. Did you get any inspiration? Or did you look at the guy who did the Elixir sequencer drum machine project in doing this?
So there were two people who did the Elixir drum machine. One I met at in Chattanooga, and he was using A Play for that, and that's fine. There's nothing wrong with it at all. But there is some latency and some issues that exist here, and I don't know if it's exactly clear from what I've got going on, but in Exsynthia, when you load the samples in memory, they're there to be able to be mixed in with the audio at any time you want them to be added in there. And so I do need to reach back out to him though and say, hey, you've got all the scenic stuff of that. Maybe we can make something really gee whiz with this.
Yeah, I've experienced the same thing with the A play latency. You're talking about like when you actually tell it to play the file from when you send the command to when it actually
Yeah.
kicks it. Yeah.
Yeah.
Yep. We've had that trouble on client, well, trouble air quotes on client projects. They have not been music specific products. It's just like, play a notification sound or stuff like that where
Yeah.
it hasn't mattered. But for what you're doing where musical timing matters, yeah, A play will probably get you in trouble for that kind of
Yeah.
thing. Yeah.
Yeah, yeah. I mean, there's not a thing wrong with it. And the nice thing is most Nurse distributions have A play bundled with them, so there's not a lot of drama to get it set up.
Yeah, absolutely.
And maybe there's a mini version of Exsynthia which says, "Hey, load up all your samples and then just give me a simple way to trigger them." That avoids a lot of that latency. We'll see.
And you said, if I got that correct, from towards the end of your presentation, you've got the ability to do lookup tables, so you could load a bunch of stuff into a LUT, and then you can play back from there.
Yeah.
Okay. Cool.
Yeah. Yeah, and some of it is just arbitrary choices. There's 99 slots for loading wave files into it, and 24 voices, so you can go wild with with all of those things. The sine wave and the fundamental waveforms that I've got in there, they are calculated samples that are just built when you run the program. But yeah. If you want a lower latency stuff, talk to me. We'll see what we can come up with.
Have you measured the latency on it right now?
So there's two things that are going on here. Parsing the characters that are going into playing. There's a little bit of time that's associated with that. The limitation is really when you create your audio callback ahead of time, you have to say what buffer size do I want to ship out there. I've got it set up so that's 1024 frames, which is a frame is a 16-bit quantity. So that means that at 440 hertz, or 14,100 hertz, I can't remember. I've done the math. I've got a spreadsheet here, but essentially you have to tune what your buffer size is with what your sample rate is, and I've run this buffer size all the way down to 512 bytes, and it seemed to be okay. Your mileage might vary depending on the speed of your system and what kind of ALSA drivers you got in place there. But like I say, offline, I'll pull up my spreadsheet and give you a number for what the latency is. And there were some attempts at instrumenting the ALSA version of my code where I would say, hey, what is my overhead of doing this synth calculation and what's going on there? I will tell you, if your buffer size isn't that big enough, you get some nasty gurgling and crackling. You guys have probably heard this before.
Yeah, absolutely. Yes, I came from the audio industry before switching into, well, anyway, long story short, yes. There's the trade-off there that I was kind of wondering about with the trade-off between, buffer size being too small and you get the crackly artifacts and the horrible, garbage that comes out versus if it's too long, then if you're trying to put that into other live stuff going on, you start getting into like the Haas zone, you start hearing like slap back, slap back from stuff being out. Yeah. So like, how does your system work in that right now? I mean, knowing it's a prototype and everything right now, is it like usable live right now, or is it like, nah, it still needs tuning, but if you're doing everything inside the system, it's working okay?
For my ability to play music, it's not a problem. And here's the dirty secret too. MIDI runs at a baud rate of 31,200 baud. So you've got some fundamental limitations that, I know it was compromised in 1984 when this came out, but I don't know. And it's hard to tell. I mean, we had a conversation about this in Chattanooga. If you've got a speaker at one end of the hall and one near you, how do you accommodate for that? It's a dynamic problem that I have no good answers for.
Yeah, that gets into the art of audio.
Yeah. Yeah, and you talked about, what was it, network time protocol, not TP, what was it, the
Precision time protocol.
PTP, yeah.
Yeah, yeah,
Which
that's what.
I'm not quite ready for that, but
Yeah, that's what Dante used to sync up their audio between pro audio devices over a network,
yeah,
dedicated audio network. But yeah,
yeah. The motion picture industry has something called SMPTE, which I can't remember
yes,
what that's a acronym for, but
Society of Motion Picture Engineers, something or other. I had to know it at some point when I went through all that.
yeah, yeah,
But yes, yeah, same type concept. Just that one did video too on top of it, if I remember right.
yeah, yeah. And then MIDI does have something that's called MIDI time clock. But once again, with all the limitations of the serial protocol, I don't know how usable that is for anything that you need to have tight precision on these type of things.
I've tried to clock against it before a long time ago when I was also much less of the coder I am today, although I still probably am on the dog side of your picture. And back then, I could read from it, but I couldn't actually get. I had a little visual metronome that would go off of it, and I couldn't quite get the timing of that, of the beat to line up right based on it. But it was probably my doing. But it was interesting to work with. I'll say that.
This is obviously for fun, but it's nice to see stuff that you work on being useful to other people. So if you got any ideas on measurements to take, certainly I can give you some measurements about what I can tell what the latency is between when I ask for it to do something and what it shows back up on the speakers. That would have been a great application of having a real oscilloscope instead of a software oscilloscope hooked up here.
Yeah, if you send over measurements, I'll drop them in the description of the video when this goes up on YouTube, and everyone can see those.
Well done.
What was your biggest kind of takeaway from working on this? Or maybe like we can tailor it to this group, but like, in the beam space.
Oh, so the overarching fear that I've got is I make something that people become dependent on, and because of my engineering practices on it, that I'm going to cause problems. So I want to have a hard wall between what I'm doing for audio generation and Beam. And that really wasn't anything that I learned from any process, but it's just like I think I know where I want the wall to be on this. It's maybe a case of premature optimization. I mean, it would be nice to have a live book where you could put, a formula on the live book and it wind up showing up in audio someplace. That'd be pretty cool. And how would that be done? I mean, do you generate a waveform and ship it over to Exsynthia, or do you take the formula and ship the formula into Exsynthia and have it somehow parse that? I mean, there's a lot of places this could go. I probably go for the simplistic version where it's like, how can I pre-calculate something and play it back later? But thanks for the question. Yeah, I'll think about that some more because I don't know that I have strong justifications for a lot of the engineering decisions I've made here.
No, it's cool things. I see a lot of parallels with other things where you reach the end of like the happy path in Elixir and you have to like get there through other means,
Well, I mean,
it's like pretty relevant. Yeah.
The smart people, like, that in the XLA or all the machine learning stuff. I mean, there's some really, really smart people who have said, okay, we can do a little bit of, we can have a little bit of Elixir and then ship it off to another compiler that does that does calculations that are specific to the GPU domain. I think that's a little highfalutin for what I'm doing right now, but there may be. I say certainly in video stuff that I think that's going to be required because it's you get the situation where if you wanted to have pre-calculated video, then shipping all those bits from one place to another might be more expensive than just calculating the bits closer to where they're needed.
So you mentioned in the presentation having rewritten this in like a million different languages by this point. So I'm going to ask the leading question that there's a right answer to this question. So what's been the best language so far? And what basically led you to Elixir this time, and what are you getting out of that versus the other languages? How is kind of everything there stacked up when you're working with audio and when you're working with the CLI stuff that you've been doing, and just kind of that whole ecosystem?
All right, so I am not going to directly answer the question because it's an instinct more than anything else. But I think I'm going to continue to do the audio portion of this and see, just because Zig looks promising, but some of the things that I'm concerned about as far as doing things really quickly or being able to randomly have one thread do something it shouldn't do isn't necessarily supported by the newer languages that want you to choose a concurrency model or choose this or whatever to do what it is. And I'm just not a Rust guy at this point, so I'm not even gonna consider that. The Go version of this was interesting though, because Go, the Go story there is that I could have one executable that had all the garbage stuck in it. And this is in the sequencer part, which I haven't shown I don't have it in Exsynthia, and I haven't shown it at all, where you're wanting to play, little short bursts of this wire protocol at precise times. And there was a concurrency timer mechanism inside Go that was really pretty easy to use. And all the things that I was doing with Grand Central Dispatch, I could just do it, and it worked on Windows and Mac OS and Linux equally well. Maybe not so well on Windows because some of that timing stuff was a little fluffy in Windows. And so when I think about making the transition on the control portion of this being in Elixir, that soft real-time aspect of thing that I have an instinct that Elixir is going to serve me well for that, but it's not proven, it's not measured yet. I just know managing the code there feels a lot nicer than trying to do some hacky thing in C or in whatever language, of course. So I'll do the sound engine in C, and then the sequencing, we'll call it that, is probably going to be in some other language, and the target is Elixir.
I think your instinct is spot on there. Elixir serves itself really well for that orchestration layer. You've probably gotten into how quickly you can put together code in Elixir, and it kind of gets you at a higher level space than like the boilerplate you have to put together in C.
Yeah.
But for like the audio stuff with the precision time and being low level to the hardware and not having not only the operating system scheduler, but also the beam scheduler in your way and all that kind of stuff.
Yeah.
Having C down there can make that side really nice. So there's a really nice blend of tying those together, I think, in what you're doing.
Yeah. And this is way off topic, and I don't have the clear memory of this, but I was looking at what the kind of what's the timer wheels that are implemented inside the beam. They're very clever, but there was some minimum unit of scheduling that existed that I didn't fit my needs when I was looking at this in the beginning. So,
does the term reductions ring a bell? Because Beam also tracks like the amount of code that's been cycled through to do scheduling switches. Also, yeah.
But and I sound like all of the Java people ever, but it's like I think the neat thing we've got on our side with Elixir and Beam is that, well, if you don't have enough reductions on this CPU, let's put it on another CPU. so
Anybody else have questions for Joe? It doesn't even just have to be programming related to it. It could just be, how did you get into, what led you into this? How do you get into the musical side of things or whatever?
I'll answer that question. In elementary school, a long time ago, we were put into a gymnasium when the teachers were going smoking, and they were talking about all of this technology of the 21st century. And there was a video that showed an oscilloscope and someone using Robert Moog showing his synthesizer, and he hit a button and it made a cool sound and it made something move on the screen. And I'm like, I don't know what that is, but I want to do that. And that was probably for me second or third grade. I didn't know what I was looking at, but I'm like, I want to do that kind of stuff. So long story short, there was a period of time where my parents said, "Hey, what do you want for Christmas?" It was either a computer or a synthesizer, and they were much more practical than my artistic side. So it went towards the computer side of things instead of the synthesizer. So it wasn't until many years later where I had enough disposable income to get to buy some music gear. And then when you're in your 20s and you've got music gear, what do? You join a band. So
since you've done the programming collab with John Cotton, when's the musical collab coming out? When's your album?
We'll talk to the label. That's a label announcement, Alex. We'll put it out through the right channels.
So, and this is a distance between goals and execution for me. But I'm going to tell you this. I wanted to title this presentation. Does anybody here know the band called White Stripes?
Yeah.
They've got this song called Blue Orchid, which is it's very rhythmic and kind of noisy. And I thought I'll do a version of that song called Blue Chip Orchid. And I just didn't quite get around to it. Maybe next month I'll have it done, but I'm sure I could probably make some noisy guitar-ish sounding things that any guitar player would yell at me for doing. But
nice. We'll finally have an intro tune then to the meetup. Well, thank you very much, Joe. This was great, and looking forward to seeing any updates you have here in a couple months as you polish things up.
Cool. Thanks for listening to me, guys. Hope you got something out of it.